Okay, the second part of our lesson we're going to talk about today is graphing linear equations. So far, we have been looking at equations in one variable, but now we are going to look at equations in two variables and how the solution looks different for those. So the solution of an equation in two variables is going to be an ordered pair. So that ordered pair produces a true statement when the values of x and y are substituted into the equation. And it makes a lot more sense when we look at an example. So let me show you. If you have a question that says, decide which of the 2 points lies on the graph of the line, then what we're going to do is take our ordered pair, our x and y, and substitute these values into the equation. If it makes a true statement, then this is a point on this line. If this x value and this y value do not make a true statement here, then this point is not on this line. So let's check it out. If I substitute 4 for x, that's 2 times 4, and I substitute 3 for y, then I have 2 times 4 plus 3 equals 10. So let's simplify. 2 times 4 is 8, plus 3 would be 11. 11 does not, in fact, equal 10. So this is not a true statement. So this is not a point on the line. Let's try this point. Let's substitute -4 in for x and 18 in for y and see if this makes a true statement. 2 times -4 is -8. -8 plus 18 is positive 10. 10 equals 10. That is true. So -4, 18 is a point on this line. So this would be our correct answer for this one. This should bring back fond memories from chapter 3, where we were solving equations, solving for y to write the equation in function form. So let's just review that process real fast. If I want to solve for y, I need to get rid of this multiplication here, and I need to get rid of the 10x. So I'm going to use inverse operations and start by subtracting 10x from both sides of my equation. 10x minus 10x, those are additive inverses, so that is 0. So all I have left over here is -5y. Over here, I have two terms that are not like each other, so these cannot combine. So I'm going to write it as -10x plus 25. Now to get y by itself, I'm going to undo the multiplication by using division. So I'll divide both sides by -5, which leaves me with y equals -10x divided by -5 plus 25 divided by -5. As I simplify this, a -10 divided by -5 is +2, and a 25 divided by -5 is -5. So when I solve the equation for y, I get y equals 2x minus 5. Now sometimes I will have to take an equation and solve it for y so that then I can set up a table of values and graph this line. So let's take this equation, y plus 2x equals 6. If I want to solve for y, then I'm going to subtract 2x from both sides. And I get y equals -2x plus 6. So now I'm going to make a table of values, x and y, and I'm going to use the numbers -2, 0, 2, and 4 for the domain. I'm remembering that my domain are my x values, the same as my inputs, the same as the independent variable. So I'm going to substitute these values into my equation for x. So y equals -2, and I'm also going to substitute a -2 in for x. -2 times -2 is +4. 4 plus 6 is 10. So when x is -2, y is 10. So on my graph, I'm going to start at the origin and go left 2 and up 10, 2, 4, 6, 8, 10. And now let's substitute 0 into my equation. Y equals -2 times 0 plus 6. -2 times 0 is 0. 0 plus 6 is 6. So from the origin, I go over 0 and up 6. Now let's substitute +2 into our equation for x. So I have -2 times +2 plus 6. That gives me -4 plus 6, which is a +2. So when x is 2, y is 2. So I can go over 2, up 2, and put my points. And finally, I'm going to substitute 4 into the equation. So y equals -2 times 4 plus 6. That gives me -8 plus 6, which is -2. So when x is 4, y is -2. So I will go over 4 and down 2. Now I'm going to connect my dots with a straight line and arrows on the end to show that this relationship goes on and on in both directions. Now, sometimes you will run into some special functions and they behave in kind of a unique way. So we need to use 3 points to graph each function. So these equations look very different. All I know now is that x equals 3. So I might be thinking, okay, if I start at the origin, x equals 3. So I'm going to go over 3. And I'm counting by 2's here, so I'm going to go halfway in between 2 and 4. So if x equals 3, it doesn't matter what my y value is. If my y value is 0, x is 3. If my y value is +2, x still equals 3. If my y value is -4, my x value is still 3. So when I have an equation that says x equals 3, that means my x values are always 3. So this graphs a vertical line at x equals 3. In contrast, if my equation says y equals, then all of my y values are going to be +1. So from the origin, I'm going to go over 0, but up 1. But I could also go over 6, and my y value is still going to be +1. Or from the origin, I could go left 2, and my y value is still +1, which gives me a horizontal line at y equals 1. Sometimes I'll be asked to graph a function with a given domain and then identify the range of the function. So here's my function, and my domain says x is less than or equal to 0. So I need to first solve for y, which fortunately has already been done for me, and now I can set up a table of values for x to solve for y. So in my xy table, what I know is that x is going to be less than or equal to 0. So I'm going to start my x values at 0. But all of the other numbers I list in my domain need to be less than 0. So I'm going to continue to count down here. So I'm going to use -2, 1, and 0 for the domain because of this piece of information. Now I can substitute into my function and find my matching y values. So if I put 0 in for x, -3 times 0 is 0, plus 1 is +1. So I can go from the origin over 0 and up 1. If I substitute -1 in for x, that's -3 times -1, which is +3, and +1 makes 4. So from the origin, I can go left 1 and up 4. Paying attention to my scale, I'm counting by ones on the x and y axis here. And finally, if I substitute -2 into my equation, that's -3 times -2, which is +6 plus 1, which is 7. So I'm going to, from the origin, go left 2 and up 7. Which really brings me beyond where my scale allows me to go on this particular graph, but we get the idea. I can connect these points in hopefully a somewhat straight line. And this time, actually getting ahead of myself, as we connect these dots, we need to have an end point where x equals 0. So as we come here, we can actually end our graph because our domain said that x is going to be less than or equal to 0. So this closed point here tells me that I'm including 0, but I'm not going to go beyond x equals 0. So my line extends off in this direction as a ray with the specific endpoints. So now I have graphed the function, but I also need to come identify the range. So in this case, as I look at my graph, and I can also see in my table that all of my y values are equal to 1 or greater than 1. All of my y values extend up in the positive direction, and 1 is the lowest that they can go. So as I'm listing my range, what I would say is that y is going to be greater than or equal to 1. In the same way we defined our domain as x is less than or equal to 0, and we translated that into these values in our table, that helped us identify the very smallest that our range could be as it extends higher and higher. So our range would be y is greater than or equal to 1. And finally, our last piece is to look at another real-world problem. So we have a plant nursery. A gardener at a nursery is filling pots with soil to prepare to transplant seedlings into these larger pots. Each new pot needs about 27 cubic inches of soil. The amount of soil, S, in cubic inches it takes to fill P pots is given by the function S equals 27P. The gardener is filling the pots from a bag of soil that contains 3,456 cubic inches of soil. Graph the function and identify its domain and range. How many pots can be filled from the bag?